Hello, my name is Nikos Ευθυμιάδης and I am happy to present you our work titled Crafting Distribution Shifts for Validation and Training in Single Source Domain Generalization. In the traditional recognition task, the training set is from one domain, the validation set is from the same domain, and the test set is also assumed to be from the same domain. Under this setup, if a method is tested on an unseen domain, it is not expected to work because of the distribution shift. The task in which the training set is from one domain, the validation set is from the same domain, but the test happens in a number of different inaccessible during training unseen domains is called Single Source Domain Generalization. In this context, the domain of the training and validation sets are called the source domain, and the unseen domains for testing are called target domains. But why do we need to validate on the source domain? Well, if we had access to a second domain, we would have used it for training as well. Then we would have been under the multi-source domain generalization task, and here the leave one domain out cross-validation is a valid option. So the only case we need to work under the single source domain generalization framework is when we have no access to another domain. Therefore, assuming access to a second domain for validation defeats the purpose of the task. In this work we propose a validation protocol for single source domain generalization that captures the generalization abilities of each model while having access only to the source domain, and a single source domain generalization method that is the state of the art in 4 popular generalization datasets. Let's start with the proposed validation protocol and specifically with the immediate goals that a validation protocol should have. Before we try to create a method that works, we should have a way to validate if it works. In other words, a validation protocol should exist. The model selection must be according to the validation protocol. That ensures fairness. Finally, the minimum requirement for a fair validation in order to be useful is to have some correlation with the test performance. Now the question is the source validation set useful for generalization as is? Let's examine the case of 3 datasets. The first dataset is PAX. In this scatterplot, every point is a model that is trained with different combination of augmentations and a different use of edge detection to enhance shape bias. The x-axis is the validation accuracy in the source domain, and the y-axis is the average test accuracy on the unseen target domains. The validation protocol proposes the rightmost model. In the case of PAX, the validation accuracy is saturated, and for the proposed models we have no guarantee that they will be good. Specifically, we can say that the chosen models can be as bad as almost 40% test accuracy, all the way up to almost 80%. In mini-domainnet, the validation performance is not saturated, but this region with the seemingly top-performing models include models that are underperforming on the test set. Also, if we limit our experiments to AlexNet, the top-performing models in the validation are the worst in the test set. Finally, on the digits dataset, we observe no correlation whatsoever between validation and test. Also, the top-performing method in the validation is underperforming on the test. So, what do we propose? We propose to augment the validation set. We use the library imgaug, which is a huge augmentation collection, and we use all the augmentations available. Specifically, we use 76 kinds of augmentations that were grouped to 10 categories, and we randomize the hyperparameters. We ended up with a validation set of 10 times bigger than the original in 10 discrete augmentation groups. Returning to the correlation scatter plots with the proposed validation set, we observed strong correlations everywhere. Additionally, we demonstrate the capabilities of the proposed validation protocol in the case of real methods from the single source domain generalization literature. Validating on the standard validation set on the left show no or negative correlation with the test, while the augmented validation continues to show strong correlation. In a realistic scenario, the rightmost model would have been selected out of the pool of the trained models. This is a comparison of the selected models of the standard validation versus the selected models of our augmented validation. In PAX, we observe a 22.2% increase in test accuracy and in mini-domainnet an increase of 7.3%. This huge increase happened just by validating in a better manner. In the case that a method uses an augmentation that we use for validation, we propose the following cross-validation scheme. The method should use the first half of augmentations for training and the second half of augmentations for validation. Then it should use the second half for training and the first half for validation. Finally, the method should be trained with all augmentations, and the decision is made on the average of the two pre-calculated augmentation performances. As a single source domain generalization method, we propose the following pipeline. In training, as a first step, the image is augmented, and binary thin edge detection is used in order to increase the shape bias of the model. Both the augmented image and the edge map are passing through the network, and cross entropy is calculated for each output. The final loss is the weighted sum of cross entropies with a lambda parameter. In inference, if it is in validation, the image is augmented. Both on validation and test, the edge map is extracted, and both image and edge map are passing through the network. A test time parameter W is used as a power to the logits. Finally, the logits are multiplied. We also present our ablation study. We report the accuracy of the vanilla training on the source domain. By adding the binary thin edges on training, we got an increase of 14.4%. Adding edge maps in the inference increases the performance by 1.1%. Finally, adding augmentations during training increased the performance for 2% more. The proposed method is the state-of-the-art in 4 popular generalization benchmarks. Thanks for your attention.